So thanks everyone. It's great to be here. Great to be talking on this topic, following up some people speaking about these specific systems. So this is a project that's been quite interesting. It's been a collaboration between where I work at the eScience Institute with folks in the astronomy department at UW, at the DIRAC Institute, at the Paul G. Allen School, the UW Database School, and our group in the Paul G. Allen School. It's kind of this interdisciplinary thing where we decide to explore what we can actually do with various distributed systems in a scientific context. And I should point out that if you want the real technical details of this, there's this paper that's preprint is available right now. It's going to be presented next month at the VLDB, the Very Large Database Conference in, I think in Germany. And so if you want more of the kind of research side details, you can look at that paper. I'm going to give more of the kind of SciPy community aim of this. So I want to start out and tell you one thing that's been interesting. I had my training in astronomy, so I had my academic upbringing writing astronomy papers. And then I started working with CS people. And CS papers are a little bit different than domain science papers. And so I just wanted to give you a little guide of how to write a CS paper. So the first thing you need to do is find a well-defined computing problem. So you come up with a statement like, efficient generation of Fibonacci numbers is a perennial problem in computer science, and no agreed-upon standard solution yet exists, right? So you frame it well with something that everybody can understand. And then you write a system that solves that problem, and you write something like, we present FibDB, the first ever relational database specifically designed for the generation and storage of Fibonacci numbers. Right, and so that's the start of your paper. And then, of course, you have to compare it to Hadoop and show that you're 1,000 times faster. Right, that's vital. And the most important thing is to have a bar chart with log scales that shows how much faster you are, right? And this is how computer science papers are generated, generally. And then, of course, you repeat until you're tenured. It's the best thing. And I apologize to my CS colleagues. But that's a little bit tongue-in-cheek, but this is kind of an observation that happens. This is sort of the computer science's corollary of the open science and reproducibility problems that we have in the domain sciences. In CS, it's pretty well known that the lowest barrier to entry type of paper you can do is just do something, generate the paper, and move on, and the tool you've talked about doesn't really get developed. The same way, when we generate a science paper, maybe the tools and the results we've developed don't carry on in a way that other people can use. So to the credit of my colleagues at UW in the computer science department, we've been, we got together to write this paper to try to actually address these scalable systems in a way that would be useful to scientists. So the goals of my talk are to distill these sorts of lessons from this paper that's a little bit dense for the SciPy community who's a community of users rather than builders of these systems for the most part. And I want to give you a general idea of the strengths and weaknesses of each of these systems that we looked at. And so we decided to focus specifically on scaling of image-based analysis because that's a big thing in many fields. And the two case studies that we looked at were a neuroimaging case study and an astronomy case study. So basically, think you have dense arrays of data and you're trying to do some sort of computation at scale with them. And the problems that you face here are pretty well known. Individual images are big, so they don't fit into relational databases very well, right? Relational databases don't work with 80 megabyte chunks of data. They work with tables of values. And their images are generally stored in these proprietary formats that don't interact well with tools. They require kind of specialized operations that know about the image format. They know about the arrays of pixels. And you need some sort of specialized analytics that often is developed in these domain-specific tools. So it ends up being a really difficult problem to take an image analytics workflow from some sort of domain science and stick it into one of these databases that is available out there, one of these scalable architectures out there. So as an example of one of the case studies, for the neuroscience case study, we had this three-step process. Number one, we have these images, these DMRI images of the brain, kind of think of them as like 3D scans of a brain. And first we wanted to separate foreground from background, so this is kind of a segmentation problem. Then there's a denoising problem that kind of looks at local patches and does some sort of mean to filter it and remove noise. And then there's a model fitting problem where you're looking at each individual voxel in that volume and doing some sort of tensor model to learn about the brain that you're looking at. And so that's the case study that we used, neuroscience. We also looked at an astronomy case study. And these are the 5 systems that we decided to evaluate and try out these case studies. So number one, you may have heard of some of these. SciDB, we chose this because this is actually one of the few database architectures that's specifically built to work with dense array-based data, n-dimensional arrays. We decided to look at Spark because it's a very popular system that's very well supported and has a nice Python interface. We worked with Myria mainly because it's developed by our group for this sort of purpose, for working in domain sciences. It's a shared nothing database management system. We worked with DASK because DASK is kind of the Python community's answer right now to scalable scientific computing. And also TensorFlow, because everybody seemed to be talking about it, right? So TensorFlow, I should say, is not specifically designed for this sort of thing, but we thought it would be interesting to see if we could force fit our problems onto the primitives that TensorFlow provides. So just as an interesting point of comparison. So what we did is we got our group together. We got a few domain experts to give Python reference implementations of the pipelines. And then we had folks from the computer science groups go out and try to reproduce each of those 2 case studies in each of these 5 systems. So it was a long process and very painful in some ways. And I want to go through and kind of give you an idea of what our results were. So number one, this is SciDB. This is kind of what SciDB looks like. And if you're using SciDB, the language that you use for it is this. You can either use this array query language or array functional language that they built in. We, a few years ago in my postdoc, I wrote a Python wrapper that gives you kind of a NumPy syntax on top of SciDB. So we ended up using that. And you can see here, it's basically you connect to a database, you create some array object that's distributed on that database, and then you can do NumPy-like operations on it. So here we're taking, at the bottom line, we're taking the mean and the 3rd dimension of the array. It supports user-defined functions, UDFs, via the stream interface. So if you have custom code that you want to apply to that data, you can stick that in there and it'll parallelize it. And the data has to be ingested as a CSV file. Now, the nice thing about SciDB is it has this built-in understanding of dense arrays. So in theory, it would be able to do things very efficiently on image-based data. The challenges, though, are that SciDB doesn't really have the primitives that you need to do all the things that we'd like to do to our arrays. Like, for example, you can't do a convolution in SciDB. So a convolution ends up being this user-defined function that's then passed to the data. SciDB distributes that, but it can't reason about the contents of the convolution and speed things up within the database. So you're basically just sending a Python function around. Other challenges with SciDB is all the data is passed around between workers in TSV format. So you're constantly serializing your data to TSV, then deserializing it to compute, and then serializing again. That ends up being a huge overhead. So that's SciDB. Spark is an interesting one. It has a nice Python functional API where you can plug in Python UDFs directly into this API, and it distributes them. It takes that code and runs it on the data that's distributed in the cluster. And the data is in this resilient RDD, resilient distributed data set format that's actually quite convenient to work with. It's really nice because you can use arbitrary Python objects as keys. You can do straightforward Python UDFs for these sort of implementations. The functional programming style is really nice to work with. It has a large user community, so whenever we ran into problems, we could go and there's like answers on Stack Overflow that tell you how to solve your problems. A few challenges is that it makes some decisions about caching data and intermediate results that you sort of have to tweak manually depending on your pipeline to make it efficient. And in general, to tune the resulting pipeline beyond the initial implementation was pretty difficult. There wasn't any sense of automatically tuning to speed up your workflow. Okay, so Myria, this is a database that's it's based on SQL. It provides a hybrid declarative imperative database language. This was a database designed by the UW database group to work with scientists and has had some really interesting applications in oceanography in particular. It has built-in support for Python UDFs. You can see that the way that you interact with it is not some sort of Pythonic wrapper. You're just basically passing strings of this MyriaL language around, which is not so convenient if you're not familiar with MyriaL, but if you have people sitting around who wrote MyriaL, it's better. And in general, the data is passed around with this flexible blob format. So data, basically the blob can contain a NumPy array. So there's no data serialization or deserialization that's happening as you pass data around. It's really seamless that way. And the nice thing about Myria is it's designed so that we can directly leverage these existing reference implementations of the various scientific workflows we're doing. And this, the declarative imperative syntax is interesting because you can do things like you can write explicit loops in your query code. If you've ever tried to do a loop type thing in SQL, it's pretty painful. And the Myria language is interesting that way. The challenges, though, are that in order to attain efficiency, you really have to re-implement your pipeline in MyriaL. So it's kind of this difficult translation process. So we ended up not doing a whole lot of stuff in the native Myria language, but we use these, again, Python user-defined functions that were passed around, similar to the way we did it with Spark. And again, the tuning for Myria is a little bit difficult. It's not automated. You have to understand a lot about the guts of the system in order to figure out how to make your code go faster. Okay, another system, DASK. We just heard about this a little bit earlier if you were in this session for Matt's talk. DASK is nice because it's a pure Python system. You write Python code. It's created by people in the Python universe, so they know how we like to think about our code. You can put arbitrary UDFs in there via this delayed this delayed syntax, and the data is literally anything Python can handle. So DASK is nice in that it's very seamless to get up and running on your own scientific pipelines. It's the deployment and installation is a breeze for DASK. This is not true of some of the other ones. The built-in UDFs, but some of the challenges are you have to. Sometimes you need to choose when to insert evaluation barriers in your graphs so that you'll get kind of intermediate results. You have to choose how to manually partition your data. You know, DASK isn't a relational database like some of these other systems. So you're in charge of, for the most part, taking care of your data and distributing it to different nodes. The person who was implementing the DASK interface found that there were a few choices between like futures and delayed that were tough to make. It was hard to know when to use one versus the other. So there was a lot of tuning, and sometimes when DASK fails, it fails in a way that's difficult to debug and requires kind of restarting the whole job. So we were working on that a little bit. Now finally, the last one, I've been like rattling off all these features. The last one is TensorFlow. TensorFlow is interesting because, especially for this task, because it's not really designed for the task that we were doing, like I mentioned before. But you basically you can use Python to set up the TensorFlow workers. User-defined functions in TensorFlow are just not supported. TensorFlow has this model that everything you do is going to be a TensorFlow operation that's built into the TensorFlow system. And the data is this TensorFlow specific structure, and the real challenge with with the data, the data on TensorFlow is everything needs to be loaded via the master node, and then it's distributed from there to the workers. So it causes this real network overhead because you can't, if you have hundreds of gigabytes of data, you can't tell the workers to load that data individually. It all has to be instantiated on the master node and sent out. Advantages, we didn't really find any for this, for this application. I should say that I want to make clear that we were pushing TensorFlow way beyond what it was designed for, so it's kind of unsurprising that we didn't find it to be a good system for this task. But TensorFlow is an amazing system for what it was designed for. But we thought just for completeness, it would be interesting to explore it. The challenges, like it has limited support for distributed computation, so you have to do all the sort of mapping of data and code on your own. It has this graph limit of 2 gigabytes that meant we ran into places where we had to chunk our operations kind of by hand. It has no Python UDFS, so everything needs to be re-implemented in the TensorFlow language, which is not complete, so we weren't even able to finish the astronomy pipeline in TensorFlow, for example. And it has this limited set of built-in operations, like you can't do element-wise data assignment in the tensor arrays, or in the tensors, which for things like masking and filtering just didn't work. So it was an interesting experiment, but TensorFlow is not made for scaling arbitrary scientific pipelines. So we did this all of these, and we ended up with some benchmarks. And the benchmarks kind of, I'll give you the broad end-to-end one for the neuroscience use case. Basically what we found are that DASK and Myria and Spark were all comparable. And the reason for this is that essentially they were all doing the same thing, right? Because we weren't able to translate our pipelines into the native languages of each of these systems, all they were doing were passing around Python functions and applying those to data in the various ways that they store their data. So it's not surprising that they're all similar. TensorFlow and SciDB were quite a bit slower than the other 3 systems. And the main reason for this in both cases was issues with passing data around between nodes. With SciDB, it has to be serialized to TSV and deserialized every time, over and over and over again. With TensorFlow, it all has to be loaded in the master node and broadcasted out. So a lesson for this is if you're developing a distributed system, make sure the nodes themselves can ingest the data rather than having to send the data over the network. We have a whole bunch more benchmarks. I don't want to dive into these because it goes into a lot of the details of the different steps and things like that. So if you go check out the paper, you can read about that if you're a little bit curious. But I just want to kind of, as broad takeaways for this audience, who I assume is mostly scientific practitioners working on domain science, interested in scaling your scientific analysis, I want to give these kind of key takeaways. So the first thing is that none of these scientific pipelines provide a complete enough set of primitives that you can expect to put your scientific pipeline into the native language. For Dask, it's not designed to have its own primitives. It's designed to just pass around Python functions essentially. But for the other ones, none of them, we were hoping that we would be able to completely implement one of these use cases in, say, MyriaL language or in the SciDB array query language, but it just couldn't happen because they're not flexible enough. So what this means is that if you want to do science at scale, user-defined function support is essential. And so all of these except TensorFlow have some form of Python UDFS support where you can pass your Python functions, whether it's from scikit-learn or scikit-image or the LSST stack or from DiPy. You can take these functions that are well tested and you can distribute them out to your data that's sitting on these various compute nodes. So that's essential. One thing that's incredibly important is flexible data formats, right? We saw that SciDB and TensorFlow had these bottlenecks mainly because they handle data in a strange way. And Dask and Myria and Spark all do this well, and we're able to kind of work with data efficiently. Automatic tuning, this is something that, especially for the scientific user, is a real issue, right? Because if I'm designing a database system, I shouldn't I shouldn't require that all my users have an encyclopedic knowledge of all the little decisions that are being made inside that database. Like, the kind of holy grail is to just, you start it up and it should work on your task. And none of these right now are doing well as far as automatic tuning of these sorts of workflows. There's still a lot of little nitty-gritty details you have to choose yourself. Streamlined installation, I think, is really, really important because I don't know about you, but when I'm trying a new tool, if it takes me over an hour to install, I give up. And as someone who's worked on SciDB, I spent a year working on various things of SciDB. I still, at the end of that year, I couldn't install it in less than half a day. And so since then, I've just not used SciDB, mainly because of that. So installation is important. And then the large user community, I think, is key too, because you're always going to run into issues with these database systems as you're scaling workflows. And if you can find those answers on Stack Overflow, then or other communities, it's really, really important. So this doesn't paint a very good picture for scalable computation or scalable scientific workflows involving images, right? There's no one tool that kind of shines above all the rest. But I think the interesting thing about this is that this study, it's being presented in this database community conference. It's one of their top couple conferences in that community. And what we're really hoping we'll be able to do with this is take this paper and kind of point to database researchers the types of problems that real-life users are having. So someone beyond the grad students that's running the benchmark for their latest paper in a CS conference. Our hope is with this paper that we'll kind of, by outlining all these tough parts, these issues, and outlining the problems that we had in applying these to real-life situations, that it'll pave the way for improvements in the future. And in particular, the UW database group who I'm working with has some plans to kind of build off this study and start thinking about how we might create a scalable computation system that really is geared towards the types of data that we as scientists are using. So keep up with that, and hopefully I'll have a little better story about scalable science in a year. So. Thanks very much. This is my contact info, and I have the paper preprint there, the slides, and if you're wondering about the code behind all of these benchmarks, it's all in a private Git repo, but we'll be releasing that later this summer, I hope. So, thanks very much.
So any questions?
Hi, thank you very much for this work. I have a data set of 1 billion images, and
I'm sorry.
I know, right? They've been coming in for 10 years, and they come in at a rate of about 5 per second. I have a batch workflow, and I have some code and Celery wrapped around it. And I'm wondering if you can comment on the difference between the systems you looked at and a traditional batch workflow.
By batch workflow, you mean just passing batches of data and then saving the results? Or?
I mean, not automating the process of distributing workers and using a system that manages communication between them and scheduling.
Yeah,
it's kind of a base case, right?
Yeah, I guess we could have done that. I don't really have many thoughts on that, but
because the question is that a viable solution compared to these?
I guess I think, yeah, at this point I would say, because we're not really, in all of these, we were not able to leverage the kind of efficiencies that these systems build in, except with DASK, DASK is sort of designed for this kind of stuff. But with the other systems, we weren't really taking advantage of the efficiencies they have built in. So I think it would probably be comparable to kind of a cron job for your batches. Yeah.
Hey, Jake, thanks for the talk and thanks for the work.
Yeah.
I guess my question is almost related to the previous one. I find it interesting that you're looking at it from a database point of view. When I think database, I think inverted indices, I think information retrieval problems, maybe data partitioning. That's where maybe you overlap. So is this a database problem?
Well, it is in the sense that you have these databases like SciDB and there's another one that starts with R that I can never remember that are like actually built for dense array data. So the hope with SciDB has been that SciDB could shine in this sort of situation, but what we've found is that its built-in database operations just aren't comprehensive enough to cover our workflows. But so that's why we didn't call this a survey of database tools. We called it a survey of what we call big data systems, and we have some little footnote where we talk about what we mean by that, which is basically systems that try to do computing at scale in some way.
Thanks.
Yeah.
Yeah, it was a nice talk. Learned about some new tools I probably won't end up using. But yeah, I was wondering, one of your kind of bottlenecks was a flexible data format. And for example, when I work with collaborators, what I found is for image data, simple HDF5 would work very well. And you can read it with DASK. There's parallel HDF5. You can read it into TensorFlow, distribute the stuff. And I was wondering what your take on such a more common format would be that you could share among researchers with maybe different tools, even across languages.
Yeah, it's a great question. So I love HDF5. I think it's having that sort of standard cross-domain tool is awesome. The problem is that you have so much inertia in these various fields. Astronomy has used fits for 20 years, and you're gonna pry fits out of people's cold dead hands, right? That's just what they use and what they're familiar with. And it's similar in neuroimaging. They have these formats that work, and it's hard to convince a field to move over to something new just because the folks on the other side of campus are also using it. So I think there's two approaches to that. You can try to change the community to make it more amenable to the tools that are available, or you can try to build tools that work with the standards used in each community. And I think computer science has been trying to do the first one for too long and needs to spend more time on the second one, adapting the tools so that it can work with people's current workflows.
Yeah, thank you.
Yep.
Hey, really great talk. At the very beginning of your talk, you mentioned that this is very challenging because all domains of science are very specialized, and you need domain-specific knowledge. It seems like a lot of these tools to use efficiently, you also need user or domain-specific knowledge. Like for example, I know TensorFlow allows you to do custom functions, but you have to write them in C++.
Yeah.
Do you have any? I know the first problem is really hard, trying to remove science domain specific. Do you have any thoughts on how we could maybe try and reduce the burden of these tools?
Yeah, so I think it comes back to that auto-tuning thing. You can, there's actually people who are spending a lot of time researching this in the database world, because auto-tuning of databases is like a hot topic. And so I think if people on the database side can gear their research towards the types of problems that we have, towards these kind of case studies, which are pretty representative of the things we face in science, I think that will lead to better tools in the long run. And so that's why I'm encouraged to have this group at UW. It's a really well-known database group starting to think about this and starting to encourage their field to think about it. So I'm optimistic, but like I said, we're not there yet.
Are there any other questions? No, so let's thank Jake again.